because I didn't know whether you would be in there or not. I didn't want to block you from being able to get in there.
Oh yeah, I think I think you can, as long as we both don't submit something.
Oh, okay. Well, to be safe, I won't go in there. It really would not have done me much good at any point, now that I think about it. All the mistakes we make are either arithmetic mistakes or calculus functions that I wasn't familiar with, even if I had seen them before.
Yeah.
So we want to go question 5. Is that the one we ended on?
Yeah, that was the one that we both wanted to punch the computer after.
Can we start somewhere else? I hate to take up a half an hour. If I remember right, that was a huge amount of algebra and arithmetic.
Yeah, it was.
And that's all it was.
We could just go to question 6.
Let's go to 6, just so we don't start off with such a frustrating.
Easy.
It wasn't a particularly hard problem. It was just the numbers they had put with it made the calculations.
This is the last homework, so and maybe depending on how far we get, I might have to call you again, but depending on how far we get today, we may not even need another session.
Okay. All right. Let's see. So we're doing solids of revolution. Okay. Good. How much have you been taught on solids of revolution?
Little to none.
Okay, because this tends to probably be the most confusing subject for new calculus students.
Okay.
You have to be able to, first of all, picture the solid of revolution and then figure out how you're going to chop it up. And by that, I mean in much the same way that we take the area under a curve and we chop it up into rectangles or trapezoids or parabolas at the top. We have to do that with solids of revolution also. And if you were to take this function and rotate it about the x-axis, you would get something that looked like this. Kind of like an old television set. with this being the front where you would look. And if they said, well, let's figure out the volume of this solid, in other words, this is now a three-dimensional solid, and what we would want to do would be to chop it up into round discs, kind of like coins, and then add the volume of each of those discs up.
Okay.
Well, what is the volume of one of those discs? If I gave you a three-dimensional coin, I don't know how to draw a coin.
The pi r squared plus something.
Well, it's a cylinder basically, right?
Mm-hmm.
A disk is a cylinder. So it's the area of the cylinder times its thickness. So in this case, it's pi r squared times the thickness, but the thickness is actually going to be delta x. In other words, the delta V for every single disk is equal to the surface area of that disk times its thickness. And in this case, its thickness is delta x because the thin part of each disk is perpendicular to the x-axis. In other words, when we go to integrate this, we're going to integrate along the x-axis. We're going to go from this point A to this point B. And as we go along each of these disks, the radius changes. And what is the radius equal to?
R.
F of x. In other words, if this function was, say, x squared plus x minus 1, then the radius of each disk is going to be y, or f of x. So when we go to do an integral, we're going to take, instead of pi r squared delta x, we're going to take pi f of x squared dx. And we're going to go from A to B. And that is going to give us the volume of that solid. Now, not all volumes of revolution can be split up into disks. Sometimes you have a hole and you need to use washers. And washers look just like disks, only from the outside they have a hole in it of some radius. So when we use washers, the area is the pi r squared of the outside minus pi r squared of the inside. So washers are different altogether in terms of the formula.
Okay.
And then the last object that we tend to use is called cylindrical shells. Have you heard that expression? Have you gotten to those yet?
Mm-mm.
Let's not get further than we need to. Perhaps this lesson it's only going to be disks. I don't know. We'll see as we look at these problems. So I'm trying to find the volume. Let me do this just a second. Oh, I got to be able to get it on the screen. Okay. Well, if we draw a picture, which is usually almost mandatory when you're doing these problems. So y equals 2x is a line that goes like that. Y equals 0 is the x-axis, not the y-axis, but the x-axis. X equals 0 is the y-axis, and x equal 4, we'll say, is this line right here. So they want the volume of this solid generated by revolving it about the x-axis. So the solid that we're going to end up with is going to look just like a flying saucer on its side. So how can I get the volume of that based on integration and what object to use and all of that? Are we going to use disks?
Looks like we could use like triangles.
Well, the problem is this is a curved object.
Oh, okay.
If you were looking at this would be curved everywhere on top. It's more like a top.
Oh, okay, I see it. Okay.
And so we could figure it out by finding the volume of a cone. That's one way we could do it, because that's what we're going to have is a cone, a perfect cone, in this case. But we don't want to figure it out that way. We want to use calculus to figure it out. Most of the objects you'll be finding the volumes of, you won't be able to find them with regular geometry. In other words, this is their introduction, I suppose, maybe because we could figure out what the volume of this cone was and compare it, just to prove to it that the calculus method works. Mm-hmm. But what I'm going to do is chop this up into disks. The disks are going to be perpendicular to which axis?
X.
Okay. So I got a little tiny disk right there, and then I got a slightly bigger disk there, and a slightly bigger disk there, and so forth. My artistry sucks, but you get the idea. And the volume of each disk, if you want to look at it as dV, whereas the volume of all of the whole object is the sum of all of these, but the volume of each disk is pi r squared times dx. Pi r squared being the surface area of each disk, dx being the thickness of each disk. So I can now look at this as a differential equation where I'm going to integrate both sides. Well, when I integrate the left, I get total volume. When I integrate the right, I get pi f of x squared, because it's f of x that represents the radius of each disk, dx, like that. And I'm going to integrate from where to where?
0 to 4.
Okay. So now we have volume equals the integral, and we always take the pi out because that's just a constant. F of x was 2x, so it's 2x squared dx, which is the same as the integral of going from 0 to 4, 4x squared dx. What's this antiderivative?
X squared.
Remember, we're integrating.
Oh, okay, so 4x cubed over 3.
And we're going to evaluate it from 0 to 4. So what's our answer?
Um, 4 cubed is what?
64.
64 times 4 divided by 3. 85.33. Oh, they want it in pi, though.
.256 is not divisible by 3. So that's got to be the final answer. (256 times pi. Well, I guess we could put in the decimal. What is 256 divided by 3?
I think it's that. I don't think they would have it.
Okay.
It doesn't say round. It says type exact.
I agree. I agree. We're getting the hang of this. Okay. Now, the reason we draw it is because you can also rotate about the y-axis, or you can rotate about the line x equals 1, or the line y equals -2, or anything. And when you do that, it becomes very confusing if you don't have a picture of it. So let's just make a quick rough drawing of this. Usually if they say they're rotating it about the x-axis, that means you're going to be integrating along the x-axis. Okay, the square root function, that's going to be let's see, x can be negative 2, so that's going to be shifted to the right, or left rather, by 2. So this is negative 2, and this is the square root function that we're looking at. In other words, that's f of x equals square root of 2 plus x. Here's the line x equal 2, x equals 6. So it's this part of that, it's this area that's going to be rotated about the x-axis, not the whole thing. Doesn't really matter, as all that affects is our limits of integration. So again, what we're going to use disks. Perhaps disks is all you've been taught. You haven't been taught washers yet?
Mm-mm.
Okay, we'll see if we run into a problem with washers. Washers aren't that much different. Pretty much the same concept. It's just the surface area of the washer is figured slightly different than the surface area of a disk. Surface area of a disk is pi r squared, whereas with a washer it's r squared. It's pi times r squared, big R squared minus little r squared. Okay, so this, the integral we want to set up is what?
Pi root 2 plus x squared dx.
From?
From 2 to 6.
In other words, what we're going to end up with is a shape that looks something like that, and we're going to have disks going perpendicular to the x-axis such that dx, the thin part of the disk, goes with the x-axis. Okay. And that's a pretty easy one to do. That's the integral from 2 to 6. We're going to again take the pi out, so we're integrating this. It's that integral.
That's to the negative 1/2, right? Or just the 1/2.
No, because after we squared it, remember we have to square it, because it's square root of 2 plus x represents the radius of each disk.
Oh, I see.
So then when we square it, we now have just 2 plus x. So what's the antiderivative of 2 plus x?
2x plus x squared
Over 2.
over 2.
In other words, always add 1 to the exponent and then divide by the new exponent. We're evaluating this from 2 to 6. I'm kind of curious that all of a sudden we're getting reasonable numbers to work with. In other words, they didn't give us 1.7246 and 5.94. I wonder if this software is actually capable of seeing that, of adjusting based on that. I doubt it, but it's supposed to be an adaptive learning thing. Okay, so how do I evaluate that? Which is what I have to do to come up with the volume. Sean, you still there?
Yeah.
Oh, okay.
Yeah, I think so. This one is.
I wasn't sure about
pi.
Okay, so in other words, you substitute 6 in for x, and we get 12 plus 18 pi. Okay.
And f of 2, 4 plus 2, 6 pi.
Okay. Whoops. 24 pi.
Mm-hmm.
Okay. You don't really need to keep drawing pictures for these, but the moment you hit harder ones, it's going to be real valuable. F of x equals 2x squared. Well, that's an extra steep parabola. Line y equals 0, x equal 1, and x equal 3. We'll call that 1. We'll call this 3. So it's this area here. It's being rotated to form this particular solid. Now notice that this is not a cone. This is more like a curved candlestick holder on its side. So we would have no way of geometrically figuring out this. We don't know how to find the volume under curves without calculus. So what's this integral going to be?
The integral of 1 to 3, and then it's going to be pi 2x squared squared.
Is that equal to? So help me simplify this more and integrate it.
Okay, so be 2x to the 4th, which would make it...
Be careful. Be careful what you're doing there. Remember what this is. This is 2x squared times 2x squared, which is not the same, is not equal to 2x to the 4th. You have to multiply the 2's together also.
Oh, 4x to the 4th?
Uh-huh. Okay.
And that would make it 4x to the 5th over 5.
Three to the 4th is 81.
It's going to be 972 over 5 pi.
As a final answer or as the first part?
First answer.
Okay. This one you should be able to do without the calculator, and you're better doing it without the calculator, the second part.
It's just going to be 4/5 pi, right?
Uh-huh. So our answer looks like 968 fifths pi, which necessarily has to be or is in simplified form. Well, actually, we could turn it into a proper fraction, but they shouldn't have any problem with this, right? In fact, didn't we give our last answer as an improper fraction?
Yeah.
No,
I don't think we did.
968 divided by 5 times pi. Okay. And we're still going to rotate this about the x-axis. Notice what this function is. That is the equation of a circle. If you square both sides, you get x squared plus y squared equals r squared. And that's the positive side of it, the part above the x-axis. So if we rotate this about the x-axis, we're going to get a sphere, right? So whatever volume we come up with better be the volume of a sphere with radius 6. So we have something to check it with. We're going to use calculus to do it. So they've drawn the picture for us. We're going to split this thing, we're going to rotate it about the x-axis, forming a sphere, a perfect sphere. And then we're going to integrate using disks from left to right, going from minus r to plus r, or in this case, going from minus 6 to plus 6. Would you like to go through that, or you want to just use the answer we know it to be? What's the volume of a sphere?
It's pi r squared times its height.
First of all, it's a volume of a sphere, so it's got to have cubic centimeter or cubic distance as its units. So remember that that should make r being cubed.
What is 4/3?
Yeah, the 4/3 pi r cubed is the volume of a cube. So since we know the radius is 6, then we can just plug it in here, and we got 4/3 pi times 6 cubed, which I believe is 218. 218 is not, is not divisible by 3 either. So what do we got? We got 872 divided by 3. It's as small as it gets. 872 divided by 3. I would have gone through the calculus way to do that if we hadn't already done 2 problems, so I know you know how to do it. Nice. Nice.
So they make us do it?
Yeah, but I don't know how they know. Okay, well, that's supposed to be the answer. Let's do it the calculus way. $872 over 3 pi. Wonder if I did the math wrong. Okay, so we'll do it the same way as we've done it before. What are our limits of integration going to be?
6 to 6.
Negative 6 to 6.
Oh, that's right.
Okay, and it's going to be what?
Are we using the semicircle one or the,
Yeah, we're going to use this one because what we're looking at here is the distance from the x-axis to the point on the graph is going to be the radius of the disk. Remember, we're going to slice this up vertically into disks, and we're going to integrate from this point, minus 6, to this point. So each radius is the y value, and we're going to square the radius because it's pi r squared, so we end up with 36 minus x squared dx. So there's our setup. So we now have 36. One other thing let's talk about. Because we have symmetry, we can do this evaluation far easier if we go from 0 to 6 and multiply it by 2.
Okay.
That's the same thing. Only if you have symmetry about your y-axis can you do that. You can't always do it. If this was a different shaped curve, we wouldn't be able to do it. The volume wouldn't be the same left and right. But in this case, it makes the problem a little easier. So now we have 2 pi times 36x minus x cubed over 3 evaluated from 0 to 6.
Why was it 2 pi just then?
Because I'm only doing a quarter of the circle, and I'm going to multiply it by 2. Because it's an easier evaluation rather than having to go from -6 to 6. I'd rather do it from 0 to 6, and because everything is symmetrical, I can do that. In other words, if I don't have that 2 in front of there, what I'm going to get is the volume of a semisphere. Because all I'm doing is rotating from here to here about the x-axis. Well, that's okay. I can take that final volume and multiply it by 2. And that's why I'm going where I got this 2 from, and why I'm only going from 0 to 6 instead of -6 to 6. So this is 218 minus 218 over 3. And
I got
notice
36 times 6 is 216.
Maybe that's where I did my problem. You're right. I think that's where I made my mistake before. What's 216 times 3? 6. I got to turn this into thirds. So that's 648. 648 thirds. So this is 2 pi times 432 over 3.
What about the cubed?
No, that's going to take care of it. In other words, if I would have cubed it right, we would have gotten the right answer the first time.
No, I'm saying like, because the 648, 36 times 16 is 216.
Well, it'd be,
you get 648.
I turned in 216 into thirds. So I multiply it by 3 on top and bottom. Because I'm having to subtract a fraction, so I need a common denominator. So 6 times 36 is 216 times 3 is 648.
Okay, so then it should be minus 6 cubed, which is
216
Okay.
over 3. And that subtraction gives us 432 multiplied by 2 gives us 864 over 3 pi instead of 872. This was exactly 8 bigger than it should have been because I made a mistake by 2 when I did my multiplication. So this is going to be correct. It just needs to be changed to this. So I'd have gotten the right answer with the 4/3 pi r cubed if I'd have multiplied r cubed properly. I just didn't.
So then how come the 2 pi just goes to pi?
It didn't. Notice that when I got 864, I had 2 pi times 432 down here on the left.
Mm-hmm.
In other words, that 2 pi multiplied this whole thing, and this whole thing here was 432 thirds. And if I plug it into this, 4 thirds pi r cubed, well, r was 6. If I do that straight away, I get the answer we ended up putting in, which was 864 pi over 3. The only problem the first time was I didn't cube 6 properly.
Okay.
Okay? All right. Find the average value of the function on the given interval. Well, when I'm looking for average value, if I have a function, say like this, and I want the average value between 0.1 and 0.6, well, that's not easy to find without calculus. How would I determine what the average value on the y-axis is between those 2 points? Well, calculus gives us a way to do it, and that is they take 1 over b minus a times the integral of the function that we're trying to find the average value on from b to a. So here's the formula that we're going to apply whenever we're looking for average value of a function. Okay, I don't know what this function, well, I could draw it, but we don't need to if we have this formula. So we're going to go from 0 to 3.
Aren't the a and the b switched? Like, isn't a smaller, so...
You're right. You're absolutely right. You're absolutely right. That's
Look at that, I'm learning.
that's right. That's the formula right there. That's the problem.
Right.
And so b minus a is 3 minus 0, so we have 1/3 in front. And we're taking the integral of x plus 1 to the 1/2 dx. Okay. Let's do that.
Okay, so it's going to be 1/3 3/2 x.
Okay, x plus 1 to the 3/2.
And then just make that 2/3.
Multiplied by 2/3, which gives us 2/6 out front. So that's 1/3 again. How can that be? 1/3 times, it's 2/9 out front. Excuse me, I was going to get us in a lot of trouble there by making a math error. And notice that we don't have to worry about what the integral of the inside is or the derivative of the inside because it's 1. In other words, if there was a 2 in front of that x, I would have to concern myself with that. I would not be able to integrate it exactly the same way. I would have to further divide by the derivative of the inside. But since the derivative of x plus 1 is 1, I don't have to concern myself with that. So we just need this answer. That's pretty good. I caught myself multiplying 1/3 times 2/3, coming up with 1/3, knowing that couldn't be right. So I had to make an error. It wasn't 2/6.
Oh, let me plug that in, sorry.
Mm-hmm.
I'm not sure how to do that without getting a decimal.
4 to the 3 halves. Do it without your calculator.
So 4 cubed.
No, always do the bottom part first. It's going to make the math so much easier. Take the square root of 4 first, and then cube it.
8.
Okay. Minus. Now, I don't need to rewrite that 2/9. All I need to do is put brackets around the whole thing, like this.
And that would just be 1, right?
Yes. So now it's 2/9 times 7, or 14/9 is the average value. Okay. Set up the integral for me.
I'm just writing this out quick. Alright, so it'd be from 1 to 2. And then 2x squared e to the 2x.
What goes out in front of here? What is 1 over b minus a?
1/2.
B is 2.
Oh, so 2.
So 1. B minus a is 1. So 1 over 1.
Yeah.
So there's a 1 out there. Okay. And I can take this 2 out there, remove it from the integral if I want, just to make it a little easier. How are we going to integrate this?
So x squared would be x cubed over 3.
Hold on. Can't integrate it like that. We don't have a product rule for integration. We can't integrate them separately. What we have is a polynomial function multiplied by a transcendental function. So when you see that, think integration by what?
Parts.
Right. Notice substitution doesn't work. If I do integration by substitution, u would be 2x, and the derivative of that is 2. That doesn't get rid of this x squared. So integration by parts is the only way to go. Now, here's my question. We can do this, or I can put it into Wolfram Alpha and get an answer. This is a iterative by parts. In other words, this is going to take 2 iterations, and the reason I know that is because this is an x squared. In other words, the first one by parts whittles it down to an x, and then the second one by parts whittles it all the way down.
Yeah, we can just do it in Wolfram because I can just do that.
Are you sure?
Mm-hmm.
Okay, because I feel like you'd learn it better if we did it all the way through, because I'm not sure you and I have done an iterative integration by parts before. So let's see if I can figure out how to put this in.
And if anything, we can just get the answer from this, and then we can go all the way through, just so I have the notes for it.
Okay. Okay. So it's 2x squared e to the 2x. 2x squared e to the quantity 2x, comma, 1, comma, 2. That's the limits of integration part. Okay, it looks like we type.
I need to use the restroom.
Okay.
All right.
Okay. It is worth pointing out that when you do a NIT, they don't do it the calculus way, as far as I know. Now, this almost appears to be different, but usually they use some sort of an approximation when they do a NIT. Either they'll use Simpson's rule or rectangular left sum. Notice that they have the approximation down here. In this case here, they appear that they knew how to take the integral of this function because they came up with 1/2 e squared times 5e squared minus 1. Now, your homework is asking for it to 3 decimals, so this should certainly be right. But the approximation, if you were to do this in your calculator, you might actually get a different number than the exact value. 132.801. 132.801.
Can you just go back to the Wolfram for a second? I want to see how you plug that in.
It's int, and then you have an argument beginning with the parentheses. Then you put in the function, and then you put in a comma, and you put in the left limit of integration, comma, and the right limit of integration, and in the last parentheses. You always are going to have, if you have 2 parentheses going that way, you're going to have 2 parentheses going the other way.
Okay. And where did you find the answer on this?
Right here, 132.801.
Okay.
But more importantly, they gave us the function. In other words, they integrated that as a function. They didn't do just a rectangular approximation of it. They do a Riemann sum of it right here, but they don't give us the answer. They don't know why. Anyway, we'll leave Riemann up there. Ready to go to the next?
Yep.
Okay. Let me just say a word here before we go on, because I feel bad. This gives us a uv minus the integral of v du, and this is going to look something like this after the first iteration. In other words, when we let u be x squared and we let dv be e to the 2x dx, it's going to produce an answer like this. Well, we still can't integrate that. So we have to apply integration by parts a second time to this part here. And the second iteration will get rid of the x entirely so that we'll have a uv minus a uv minus an integral of e to the 2x or something like that. So know that that's the way integration by parts unfolds a lot of the times, is you have to do multiple iterations of it in order to get a final answer.
Okay.
First iteration just knocks the power of that down. If I put a 6 there, I would need 6 iterations to solve it. And each one, you've got the problem of keeping track of your negative signs. And that's why when you solve integration by parts, the negative signs become huge, just keeping track of them. All right, let's go on to the next one here. Okay. Problem sounds complicated, but it isn't really. It's the same as telling us what is the average value of this function from 0 to 6 years. So set it up for me.
Yeah, I was trying to negative 0.060. Okay, so is this using the 1 over b minus a?
Yes.
Not sure what the limits are.
Well, the limits are going to be from a to b.
Okay.
So what's a and what's b?
A is 0, B is 6.
Yeah. I hope it's not 5. No, let's see. The first 6 years would go from time equals 0 to time equals 6. Yeah, no, that should be right. And then what's 1 over b minus a?
1/6.
Okay. So now all we have to do is integrate this function. And then they're back with the hard numbers. Okay. Well, we can defeat it if you like.
Yeah.
In fact, I spent a lot of time after our last session wondering, why did we not use Wolfram Alpha to handle all of that complicated arithmetic? Only reason I hate to do it is because I feel like it's really good practice for you. But if they're going to torture us with these kind of numbers, they're almost asking for it. We've done enough easy ones that you should know how to integrate this.
Yeah, and our professor told us that we're allowed to use sites like Wolfram Alpha to help us calculate stuff like this.
Okay.
Because like you said, this is just kind of absurd.
Yeah. Well, I realized it becomes a lot less absurd if you're using Wolfram Alpha. So I began to wonder if they don't if they're not expecting us to use Wolfram alpha, they might be. Which makes it a lot less absurd. So this is 35 plus 12e raised to the negative 0.06 x, going from 0 to 6. 1/6 nth of 35 plus 12. Oh, I guess let me just go ahead and we'll know whether I typed it in there right. That's the beauty of Wolfram alpha, actually, is that it gives you feedback on what you think you've typed in. Is that correct? I think it is. 35 plus 12e to the minus 06t. So 45.0775. So raised to the nearest, round to the nearest cent, this would be $45.08. Do you want to just real quickly integrate that for me? 35t plus what? How do we do this part here? Find the antiderivative of that.
Uh, 35t plus 12 e to the first.
No, make it the same. Remember, the variable's in the exponent, so it's an e to the x function. So the integral of this is the same thing that we're looking at, and then we have to divide by this coefficient. We have to divide by the derivative of it. It follows the same rules as other transcendental functions. If I want to integrate sine of 5x, that becomes cosine of 5x divided by 5, and it's negative, because the derivative of this becomes sine of 5x. Same with the e function. If you integrate e to the 2x, it becomes e to the 2x divided by 2. So it's always e to whatever the exponent is divided by the coefficient of the exponent. Or not really the coefficient, the derivative. It's not so easy if I make that x cubed instead of 2x. Can't find the antiderivative of 2e to the x cubed. Whole different story. But as long as it's just a single power of x with some sort of a coefficient in front of it, minus 17, then the integral of that is e to the minus 17x divided by minus 17.
Okay.
Okay.
So that would be 12e to the 0.06x t over 0.06 negative.
Over negative 0.06, yes. Yeah. Okay. I feel like you should be able to know how to do that manually, and we don't have to go through all the math of evaluating it, but you should be able to get the integral of that. I want the average intensity during the 11th hour only. Let's set it up, and then we can use Wolfram alpha to evaluate it. this is undoubtedly the function we need to integrate. The only thing we need to figure out is a and b.
So A is 0, B is 11.
That would be the average intensity for the first 11 hours.
10 to 11.
Correct. So this becomes 11 minus 10. And this becomes 10 to 11. So there's no coefficient multiplier since it's 1. And this becomes x. X times e to the minus 0.5. Going from 10 to 11. You may want it 3 decimal points, 0.055. Okay, the very first thing gives you a rate of something. That means that's the derivative function, f of x. So if we want to find out the net change of the original function, we're going to integrate the derivative function assume a 10-year period from 0 to 10 at 5% compounded continuously. Not sure I know the formulas for this. Let's see. Actually, I think I do, actually. Let's see. When you have continuous compounding, you have A equals A to the E KT. Where's R go? Do you have a formula for continuous compounding?
No, I don't.
Let me look it up.
Is that money flow at x equals 10?
500. So the money flow is $500 per year is being added.
I mean, I got the last few words of the problem.
Oh, excuse me. I'm sorry. At t equal 10. They want the accumulated amount of money at t equal 10. Hold on. I'm going to my pre-calc book, not my calculus book here. But my pre-calc book. interest compounds, it's ERT. E to the RT. And this is A sub 0. So this is the total amount. If you started with a certain amount, we could use this. But that's not this problem. The problem is that 500 is put in each year. So you don't start with a fixed amount, you start with a variable amount. Let me think about this a moment. So if I go from 0 to 10, I'm not sure I know how to do this. This might be one we have to look at, see a similar problem. Unless you know, I got a feeling there may be some functions here that I don't have the formulas for in my calculus book.
We can try to help me solve this.
Yeah, let's do that just to save time. Maybe I may be overlooking something simple, but I don't want to spend 20 minutes on it and then discover that I've wasted your time for 20 minutes. So let's do that. Okay. So the present value is the integral from 0 to t of 500 times e to the minus 0.05x. Let me just write that. Make sure you understand that. See, I'm not sure I did know that. Although, that would have been my first guess, only I wouldn't have had a negative there. So the present value is equal 0 to 10. The function is 500 times e to the negative r is 0.05 and x is 10.
Or x is point. Oh no, we already got that. Yeah.
So let's put that in the Wolfram alpha.
We'll just keep hitting a continue to see what it goes.
Right. I forgot we weren't doing the problem anymore. Okay. So that answers how we're going to do the present value. Okay, so I know how to do that. Now close that. Can we still answer that? No, it's too late, right?
Yeah.
Once you have help me solve this, and we don't know how to get help on the accumulated amount of money.
We have to put in the answer. It takes you through the whole thing.
Okay, so let's do that in Wolfram alpha and put in that answer. And then we'll be able to know what the formula is for the next one. What was this? 500 times e to the minus rt R is 10, so actually e to the minus 0.5x is correct, only I'm going to do it from 0 to 10.
And it's 800. But also, if we enter this in and then hit help me solve this to find the equation for the accumulated, it counts it as wrong.
Yeah. So what should we do?
Maybe just go through the whole help me solve this with new numbers, just like with this. So if you go to help me solve this, and then we just put in a random number just to get through it, and then we can see the equation for the accumulated.
Okay. Only we're not going to be able to use Wolfram alpha on this.
And then you can just put in like 1 just to get through the answer.
Okay. Type an expression using x as the variable. So should I put in x?
Yeah, it's fine. We don't get credit for this or anything.
Right.
And then just hit check answer again. And so that's what they want.
Okay. All right, now we're going to get the continue.
Yep. So just put in like 1 again.
Okay.
So it's the same thing, except for you have e to the RT on the outside.
I see why, too. Notice that if you take, remember when I wrote that first equation, a sub 0 was changing. What they've essentially given us is the present value, which is a sub 0. No, it's a little different, I guess. I guess it's a little different. So let's see. So this is the present value equation. Let's make sure we know what that is. Present value is from A to B of f of x times e to the minus rt or x dx. And total accumulation is e to the rt integral of our present value function. Yeah, in other words, they're telling us that our present value is the starting amount. It's like coming up with an average starting amount. Okay. Close this.
Yeah.
Can we go ahead and no, we got to, how do we get out of this?
Now we're just in the regular problem, so we just solve for this one.
So we can solve for this one? Okay.
Yep.
So the present value, assume a 15-year period at 4% compounded continuously. Okay, so this goes, let's just write this out. So present value equals from 0 to 15 f of x, which is 800, times e to the minus 15 times 0.04, which is 0.6. This is e to the 0.6. So that should be our answer. See anything wrong? E to the minus RT, T is 15, R is 0.04, so that's minus 0.6. Okay. So let's go into Wolfram alpha. Hold on.
Could you jump to the hole marker real quick? T equals 50.
Yeah, so it's exactly the same as the previous problem, only it's 800 instead of 500, it's 15 instead of 10, and it's 4% instead of 5%. So we've got what goes in front of the nent here. Let's see. E to the 800 e raised to the 0.6 power times the nent, and I'll remove the 500, and I've got 0.6 instead of 0.5, and we're going from 0 to 15. Okay, I believe that should do it. Hold on, let me go ahead and figure out what that is and make sure that we're looking at the same thing. 800 e to the 0.6 times e to the minus 0.6x. Look right?
Yep.
2429, round to the nearest cent again. So I guess that's our answer. 2429.19.
Maybe it's 2429.2.
Yeah, before we make that guess, I have a hard time believing it. Wolfram wouldn't round it.
Oh, this is the present value. You don't need 800 on the outside, do you?
Well, f of x is 800.
Oh, yeah, okay.
So I had 800. Oh, what I don't need on the outside is the e to the 0.6.
Yeah, see, this is like the compounded.
Oh, yes. So let me get rid of this e to the 0.6. So this should be right. Yeah, that comes on the accumulated value that we put that e to the RT out there. So
Yeah, that's right.
let's hope. 1333.17. God dang it. This thing's going to drive me to drink.
Does it matter if the 800 also outside of the integral?
No. Constants, as long as they're being multiplied by the function, you can take them out. It doesn't matter at all. Present value is the integral from 0 to t, which is 15, of 800 e to the minus r x. The fact that this is t and this is x doesn't matter either. 4% is 0.04 times 15 is 0.6. Just to show you it doesn't matter, I'll put the 800 inside.
And then maybe we just try 1,
Yeah,
2,
we
3,
can
0.2,
try
2.
that. We can try raising it up one more number. Wouldn't be 0.2 though, would it? Wouldn't it be 0.18?
Oh yeah.
That's our last chance on this.
Worst comes to worst, it'll show us the answer and we'll see how we rounded wrong.
Wow. What is that? Exactly 6 times?
No, 7, I think.
9023 divided by 1333.
No, it's not even 7.
It's not a whole number? Well, not sure what to do at this point. We seem to have done it exactly the way they suggested. One of my notes, I wrote down the 2 formulas for present value.
I did too. We did it right. Did we have the years right? 0 to 15?
Yeah. I'm thinking we can get the second part of this correct by just multiplying the answer they told us, 9023.77 times e to the RT. Should I do that?
Does that work? Because you have the p equals e to the 0.6 on the outside of the integral on that one.
Right. In other words, what the accumulated amount is the e to the RT times the present value. In other words, when you're doing compounding continuous, you got A equals the initial amount times e to the RT. Well, since we have a variable initial amount, it's 800 the first year, another 800 comes in the second year, that's why we need calculus. So this part right here represents the a sub 0. And that's why we're going to multiply it by e to the RT. That's the way this works from if we're comparing it to how we used to figure it out in pre-calc. So we want to take the present value and multiply it by e to the RT, which is e to the 0.6. So I'm pretty sure we can get this answer by just taking 9023.77, multiplying it by e raised to the 0.6 power. Round to the nearest cent. Oh boy. Well, this one we may have to, ooh, wow, we got 2 choices. I mean, they didn't round it to the nearest cent. More digits. There we go. So it's 16442.38.
Okay. Huh, that's really weird how... So would that be the same thing if you did 1642, or 4, whatever that is, divided by e to the 0.6?
Yeah. Yeah, we'd get this answer. But this isn't the one we answered. This is the correct answer that we found out about.
Yeah, so what I'm saying is maybe we just start with the accumulated and then divide that by e to the 0.6. Because what I don't understand is why A worked using the same equation essentially and B didn't.
I'm not sure what... I don't know why our formula didn't give us A, the correct answer.
Yeah.
But that's all I don't understand. Once we know the correct answer to A, the present value, then getting the accumulated amount is just taking that present value and multiplying it by e to the RT.
One more thing before you go. Maybe try plugging into Wolfram Alpha the entire equation for A to see if we get the same answer.
Okay. But I thought I did that.
When they did that for the present value. So for A, plug in the whole thing.
So multiply
e
this
to the
by e to the
0.6.
minus point. Okay, yeah, I got you. E raised to the 0.6. Well, this isn't going to give us a proper answer, though. Because this is going to give us our answer times e to the 0.6.
Yeah, I just want to see what it looks like so I know not to do it on Wolfram if that's what it's going to tell us.
Mm-hmm.
Yeah, it's weird.
Question is, why is this wrong? 800 e to the minus 0.6x. That has to be right. I'm baffled, but I am frequently baffled by these programs. You know, this is so new that they actually could have some bugs in there. I had another student that we used this, not the exact same software, but I think written by the same company. And we had one where it showed us the right answer, and it was a graph, and it was exactly the graph we had put in. And it refused to recognize it as correct. And I never could figure out why. So there's no totally discounting the fact that they may have a bug in this.
Okay.
Just don't know how to... I mean, we could do a similar... I would suggest you do a similar problem to try to fix this 14.
Okay.
We know the formulas. As long as you have both formulas, or do another help me solve this to find out, make sure we wrote those formulas down. They don't change very much when they change the problem. They just change the numbers.
Yeah.
They don't change. In other words, they didn't ask you about the amount earned in the 15th year. They want the total accumulated amount of money, which was the same thing they asked in the previous problem.
Mm-hmm.
So that's the only thing I can suggest is try another one, and maybe there was just a bug in the software on this one.
Okay. Yeah, I'll do that. And then depending on how I do with the rest of this homework, I'm going to try to do it tomorrow night.
Okay.
I may have to call you.
I'm available tomorrow. I'm available tomorrow during the day. I don't have golf schedule. I think I'm going to play golf on Tuesday.
Okay.
Okay.
So yeah, I'll try to do it by myself tomorrow, and then depending, I'll give you a call on Tuesday to see if we can set up another session next week.
Sounds good.
All right. Thank you so much,
Okay,
David. Have
Sean.
a good rest of your weekend.
You too. Bye-bye.
Bye.